For almost the entire history of human civilization, Uranus was just another faint point of light in the night sky. No one realized it was a planet until 1781, and even after its discovery, humanity visited it exactly once. On January 24th, 1986, Voyager 2 passed within 81,500 kilometers of Uranus and spent roughly 6 hours studying a world that had existed for 4.5 billion years. Everything we know about the seventh planet still comes mostly from those 6 hours, and the data made almost no sense. Uranus is the coldest planet in the solar system, not the farthest, the coldest. Its atmosphere drops to approximately minus 224 degrees Celsius, colder than Neptune, despite Neptune orbiting billions of kilometers farther from the Sun. Every major planet in the solar system releases excess heat trapped from its formation. Jupiter does, Saturn does, Neptune does, Uranus almost does not. Something inside the planet appears to be sealing its internal heat beneath the atmosphere, and scientists still do not know why. The planet is tilted almost completely sideways. Instead of spinning upright like the other planets, Uranus rolls through space with an axial tilt of 98 degrees, leaving one pole in continuous sunlight for 42 years while the other sits in darkness for 42 more. Its magnetic field is even stranger. It does not emerge from the center of the planet at all. It is offset, tilted, unstable, and tumbles through space in a geometry no other planet seems to share. And recently, scientists reanalyzing decades-old Voyager data found possible evidence that one of Uranus's moons may contain a hidden liquid ocean beneath its frozen crust. We make these long form space documentaries because we love this stuff, and so do you. If you want to keep exploring with us, subscribe, and we'll be here whenever you need a quiet journey through the cosmos. Let's start with the moment astronomers realized Uranus was behaving unlike any other planet in the solar system. If you could pull away from Earth fast enough, the solar system would begin separating into layers. First, the rocky inner worlds Mercury, Venus, Earth, and Mars, packed tightly around the Sun like warm stones around a fire. Then the asteroid belt, scattered remnants of material that never became a planet. Beyond that boundary, the scale changes completely. The outer planets begin. Jupiter and Saturn dominate the darkness first. Vast spheres made mostly of hydrogen and helium, swollen by gravity into giants so large they distort the architecture around them. Jupiter alone contains more than twice the mass of every other planet combined. Saturn follows behind, lighter than water in average density despite its enormous size, wrapped in rings bright enough to reflect sunlight across billions of kilometers. But farther out, the pattern changes again. Uranus and Neptune belong to a different category entirely, the ice giants. The name sounds misleading because these worlds are not frozen balls of ice drifting in darkness. In planetary science, ices refers to compounds like water, methane, and ammonia, substances that were solid in the early solar nebula. Inside Uranus, those materials exist under pressures so immense that they behave as scorching fluids and compressed exotic matter rather than anything resembling ordinary ice. Uranus orbits at an average distance of approximately 2.87 billion kilometers from the Sun. Sunlight takes around 2 hours and 36 minutes to arrive there. By the time light reaches Uranus, the sunlight touching your face on Earth is already ancient history. One Uranian year lasts 84 Earth years. Since the invention of the telescope, Uranus has completed barely more than 2 full trips around the Sun. Entire generations passed during a single season there. We did not even know Uranus was a planet until March 13th, 1781, when the astronomer William Herschel observed it through a telescope. At first, he believed he had discovered a comet. The object moved too slowly and too smoothly against the stars to fit expectations. Even its discovery arrived through confusion. Herschel proposed naming the planet Georgium Sidus, meaning George's star, after King George III. Other astronomers resisted immediately. Eventually, the name Uranus was adopted instead, drawn from Greek mythology rather than Roman tradition, making it unique among the planets. The world itself is enormous. Uranus measures roughly 50,724 kilometers across, nearly 4 times wider than Earth. Yet its gravity at the cloud tops is slightly weaker than Earth's, because the planet is far less dense overall. You would weigh less there despite standing on a world vastly larger beneath you, and by every basic expectation, Uranus should behave predictably. A planet this massive, this distant, and this compositionally rich should follow familiar planetary rules. But almost every time we measure Uranus carefully, it refuses to cooperate. There are moments in astronomy when a single number changes the entire shape of a world. For Uranus, that number is 97.77 degrees. That is its axial tilt. Axial tilt means the angle between a planet's spin axis and an imaginary vertical line extending upward from its orbit around the Sun. Earth tilts by 23.5 degrees, enough to create shifting seasons and changing daylight across the year. Uranus leans so far that the distinction between upright and sideways almost disappears entirely. From a distance, it does not look like a spinning top, it looks like a wheel. Every major planet in the solar system rotates in roughly the same orientation, poles pointed more or less upward as they orbit the Sun. But Uranus rolls through space horizontally, its poles aimed sideways relative to the plane of the solar system itself. The effect is difficult to visualize because nothing comparable exists elsewhere among the planets. The seasons become extreme. Each pole spends approximately 42 years facing the Sun continuously, followed by 42 years turned completely away from it. Entire decades pass beneath uninterrupted daylight, then decades of darkness follow behind. At present, the southern hemisphere has remained in shadow for years, while the north continues its long movement toward summer illumination, but the atmosphere refuses to behave as expected. Scientists anticipated dramatic temperature differences between the bright and dark hemispheres. Instead, the contrast appears surprisingly muted. Winds and atmospheric circulation redistribute heat across the planet, with an efficiency still not fully understood, producing weather patterns that remain deeply unusual even by outer solar system standards. The geometry becomes stranger closer to the equator. Because Uranus rotates nearly perpendicular to its orbit, the familiar rhythm of sunrise and sunset breaks down across much of the planet. A Uranian day lasts roughly 17 hours and 14 minutes. Yet for many regions, the distinction between day and night becomes almost meaningless over long periods of seasonal change. How does a planet end up like this? The leading explanation begins in the violent early history of the solar system, when growing planets collided repeatedly while competing for stable orbits. Researchers believe Uranus was struck by an object potentially 1 to 3 times the mass of Earth, not a small asteroid, a young planet. The collision was likely oblique, meaning angled rather than direct. That detail matters. A head on impact might have destroyed Uranus completely, or stripped away its atmosphere. Instead, the impact transferred enormous rotational momentum, tipping the planet permanently onto its side, while leaving most of its structure intact. But newer studies suggest one collision may not fully explain everything we observe. Some planetary scientists now favor a sequence of impacts occurring across millions of years. A simulation study published in 2018 showed that a giant collision could reproduce the tilt, but only if the impact also created a thick insulating shell deep inside Uranus, trapping internal heat beneath the outer layers. So the sideways rotation may not be an isolated feature at all. It may be evidence of a catastrophe that changed the entire planet from the inside out. Temperature in the outer solar system usually follows a simple pattern. The farther a planet drifts from the sun, the colder it becomes. Distance controls the available sunlight, and sunlight controls atmospheric warmth. It feels intuitive, predictable. Uranus breaks that pattern immediately. Its cloud tops fall to approximately negative 224 degrees Celsius, colder than any other planetary atmosphere ever measured in the solar system. Not the coldest surface, the coldest atmosphere, and it should not be. Neptune orbits much farther away, at roughly 30 astronomical units from the Sun, compared to Uranus at 19. An astronomical unit is the average distance between Earth and the Sun, nearly 150 million kilometers. Neptune receives far less solar energy, yet Neptune's average atmospheric temperature sits near negative 214 degrees Celsius, making it noticeably warmer than Uranus. A colder planet closer to the Sun should not exist. This discrepancy has frustrated planetary scientists for decades because the standard explanation for giant planet temperatures depends on internal heat. During formation, planets accumulate enormous thermal energy through collisions and gravitational compression. Even billions of years later, much of that heat still leaks outward into space. Jupiter radiates approximately 1.67 times more energy than it receives from sunlight. Saturn emits around 1.78 times more. Neptune exceeds them both proportionally, radiating nearly 2.61 times the solar energy reaching it. But Uranus barely radiates extra heat at all. Measurements suggest the planet releases almost exactly the amount of energy it absorbs from sunlight, meaning the detectable flow of heat from its interior is effectively close to zero. Instruments have struggled for years to confirm even that tiny excess with certainty. Something interrupted the normal process. Either Uranus lost most of its primordial heat long ago, or the heat remains trapped deep beneath the atmosphere where it cannot escape efficiently. Both possibilities are difficult to explain fully using existing planetary models. One leading hypothesis connects the mystery directly to the ancient impact believed to have tipped Uranus sideways. According to several simulations, the collision may have rearranged the planet's internal structure completely, creating a stable insulating layer buried deep beneath the outer atmosphere. An insulating layer means a region that blocks heat transfer. If such a layer exists, warmth generated in the deep interior would remain trapped below it, unable to rise upward through convection, the process where hotter material circulates upward while cooler material sinks downward. The atmosphere above would slowly cool over billions of years, while the deeper regions remained intensely hot. In that sense, Uranus may resemble a sealed thermos drifting through space, a world with hidden heat. But there is a problem with every explanation proposed so far. We still do not know what conditions actually exist beneath the visible cloud tops, because no atmospheric probe has ever descended into Uranus directly. Everything comes from distant measurements, flyby data, and computer simulations built from incomplete information. So the coldness of Uranus is more than a strange number on a chart. It may be the visible scar left behind by an ancient catastrophe, still shaping the planet from within. If you could descend beneath the pale atmosphere of Uranus, the familiar categories of matter would begin to fail almost immediately. Gas would stop behaving like gas. Liquids would stop behaving like liquids. Even the word surface would lose meaning. There is no place to stand. Unlike Jupiter and Saturn, which are dominated by hydrogen and helium throughout most of their interiors, Uranus appears to possess a fundamentally different internal structure. Planetary models continue to evolve, but the current picture divides the planet into three broad layers, each stranger than the last. The outer atmosphere is comparatively thin, composed mainly of hydrogen and helium, with traces of methane. Below that lies the vast middle region, thousands of kilometers deep, containing water, ammonia, and methane, compressed under enormous pressure and heat. Scientists still call these materials ices, but they are not frozen. Inside Uranus, temperatures and pressures become so extreme that these compounds enter exotic physical states rarely encountered anywhere else in nature. One of the most important is called the superionic state. In simple terms, matter behaves partly like a solid and partly like a liquid at the same time. Superionic water forms under pressures exceeding roughly 200 gigapascals and temperatures above 4,000 Kelvin. A gigapascal is a unit of pressure equal to 1 billion pascals. Under those conditions, water molecules break apart completely. Oxygen atoms lock into rigid crystalline structures, while hydrogen ions move freely through them like flowing liquid particles. The result behaves almost like metallic water. It can conduct electricity efficiently while still retaining partial solid structure. Researchers suspect this strange layer extends through large portions of Uranus's interior, possibly surrounding the deeper core like an electrically active ocean trapped inside the planet. That may matter enormously. The unusual magnetic behavior observed around Uranus could originate directly from these superionic regions rather than from a conventional metallic core like Earth's. The planet may generate magnetism through circulating electrically conductive fluids, unlike anything found elsewhere in the solar system. Farther down, the pressure intensifies beyond ordinary comprehension. Near the center, Uranus likely contains a rocky or iron silicate core heated to between 4,700 and 9,700 Kelvin, hot enough to melt iron completely. Yet, despite those temperatures, the surrounding layers appear to prevent much of that heat from escaping outward. The pressure there reaches approximately 8 million atmospheres, 8 million times Earth's sea level pressure. Under conditions like these, carbon atoms carried downward from atmospheric methane may compress into crystalline diamond structures. Laboratory experiments using powerful lasers have reproduced this process by mimicking ice giant interiors, confirming that so called diamond rain is physically plausible under Uranian conditions. Tiny diamonds may form deep inside the planet and slowly descend through the interior like mineral snowfall. Over immense spans of time, those descending crystals could accumulate into layers thousands of kilometers thick. If so, Uranus may contain more diamond material than any other known object in the solar system, but it exists impossibly far below us, buried beneath pressure, darkness, and heat no machine has ever entered. A compass works because Earth behaves predictably. Deep beneath our feet, liquid iron circulates through the outer core, generating a magnetic field through motion and electrical conductivity. This process is called the dynamo effect. The field aligns closely with Earth's rotation, which is why magnetic north and geographic north remain roughly connected. On Uranus, that relationship collapses. Its magnetic field tilts approximately 59 degrees away from the planet's rotational axis. If you stood somewhere beneath those cloud tops with a compass, magnetic north would point in directions almost unrelated to the visible poles above you. But the geometry becomes stranger still. Measurements from Voyager 2 revealed that the magnetic field is not centered inside the planet. Instead, it appears displaced by nearly one-third of Uranus's radius. Rather than emerging neatly from the core, the field likely originates somewhere higher within the interior, possibly inside the electrically conductive superionic layers buried beneath the atmosphere. The result is unstable looking. As Uranus rotates every 17 hours, the magnetic field tumbles through surrounding space in a warped corkscrew motion. The magnetosphere, meaning the region dominated by a planet's magnetic influence, twists and reshapes continuously as the tilted field spins sideways through the solar wind. Nothing symmetrical forms around Uranus. On Earth, magnetic field strength varies gradually across the planet. Uranus behaves unevenly. Some regions experience magnetic intensities stronger than Earth's surface field, while others remain comparatively weak. Charged particles moving through this environment encounter abrupt shifts in direction and strength, unlike anything observed around the other major planets. Even Neptune, which possesses a similarly displaced magnetic field, appears less extreme. Researchers suspect both ice giants generate magnetism differently from rocky planets and gas giants. Instead of relying on molten iron cores, their fields may emerge from convecting superionic fluids deep inside the mantle regions. Conductive water, ammonia, and methane, under enormous pressure, could be driving electrical currents through vast hidden layers. But Uranus introduces another possibility. A study published in 2017 used computer simulations to examine how the planet's unusual orientation interacts with the solar wind, the stream of charged particles flowing outward from the sunday. The results suggested something remarkable. During certain seasonal configurations, Uranus's magnetic field may partially collapse and then rebuild itself as the geometry changes. In simple terms, the field might switch off. No other known planet behaves this way. If the simulations reflect reality, portions of Uranus's atmosphere would periodically lose magnetic shielding altogether, exposing the upper layers directly to high-energy solar particles. That exposure matters. Magnetic fields help deflect radiation and control how atmospheres interact with surrounding space. Temporary collapse events could influence atmospheric chemistry, particle escape, and auroral activity in ways scientists still cannot fully model. And yet, nearly every conclusion remains provisional. We possess only a single close-range dataset gathered during a brief encounter in 1986. Confirming long-term magnetic cycles would require observations across decades of seasonal change, carefully tracking how the magnetosphere evolves as Uranus continues its slow orbit around the sunday. To understand this planet fully, we would need patience measured in generations. By the time Voyager 2 approached Uranus, it had already spent nearly a decade crossing the outer solar system. The spacecraft launched on August 20th, 1977, carrying instruments designed to survive far beyond the original expectations of its builders. Uranus was never the primary destination. The mission existed because of a rare alignment of the outer planets, an arrangement occurring roughly once every 176 years. During these brief windows, a spacecraft can use the gravity of one giant planet to accelerate toward the next, stealing tiny amounts of orbital momentum through a maneuver called a gravity assist. The previous alignment happened while Napoleon Bonaparte was still alive. Voyager 2 used Jupiter first, then Saturn, bending its trajectory outward toward Uranus through carefully calculated gravitational encounters. Without that alignment, visiting all four outer planets with one spacecraft would have been effectively impossible using the technology of the 1970s. On January 24th, 1986, Voyager 2 finally arrived. That same day, the Space Shuttle Challenger disintegrated shortly after launch over Florida, killing all 7 crew members aboard. Public attention collapsed inward immediately. The scientific return from Uranus, extraordinary as it was, unfolded quietly in the background of global grief. The spacecraft passed within approximately 81,500 kilometers of the cloud tops, close enough for detailed observation, too distant for direct atmospheric sampling. Even communication itself felt fragile there. At Uranus's distance, radio signals traveled for nearly 2 hours and 45 minutes before reaching Earth. A full round-trip exchange required roughly 5.5 hours. The transmission rate measured approximately 21.6 kilobits per second, slower than the dial-up internet connections many people used decades later. And still, Voyager transformed our understanding completely. During roughly 6 hours of closest approach, the spacecraft discovered 10 previously unknown moons and 2 additional rings. It measured atmospheric composition, mapped the bizarre magnetic field for the first time, and captured humanity's first detailed images of the Uranian system. But the planet itself appeared strangely silent. The photographs showed a smooth blue-green sphere with almost no visible storms, cloud bands, or atmospheric structure. Compared with Jupiter's turbulence or Saturn's layered complexity, Uranus looked nearly blank. That absence became one of the mission's most important findings. Scientists expected some level of visible atmospheric activity driven by escaping internal heat. Instead, the featureless appearance reinforced the growing realization that Uranus radiated almost no excess energy outward. The planet seemed internally dormant in ways no other giant planet did. Even now, much of modern Uranus science traces back to those few hours in 1986. Later observations from telescopes refined details, but the foundational measurements, the magnetosphere, rings, moons, atmospheric chemistry, and close-range imagery, all emerged from a single passing encounter. Voyager 2 never slowed down. After leaving Uranus behind, it continued onward toward Neptune and eventually interstellar space. No spacecraft followed, no orbiter arrived later, no atmospheric probe descended through the clouds. Humanity looked closely once, then kept moving. The moons surrounding Uranus carry names that sound less like astronomy and more like theater. Titania, Oberon, Ariel, Miranda, Umbriel. Around most planets, moons inherit names from mythology. Around Uranus, they come from literature. The tradition began with John Herschel, son of William Herschel, who proposed naming the moons after characters from the works of William Shakespeare and Alexander Pope. Today, Uranus has 28 confirmed moons, each orbiting through darkness with names drawn from plays, poems, spirits, and exiled daughters. The 5 largest dominate the system. Titania, the largest, measures roughly 1,578 kilometers across. Miranda, the smallest of the major moons, spans only about 472 kilometers. Between them lie Ariel, Umbriel, and Oberon, each carrying landscapes shaped by deep time and hidden internal forces. Titania and Oberon were discovered in 1787 by William Herschel himself, only 6 years after he first identified Uranus as a planet. Ariel and Umbriel followed in 1851, discovered by the English astronomer William Lassell. Miranda remained invisible until 1948, when Gerard Kuiper finally detected it through telescopic observation, and Miranda changed everything. Few places in the solar system appear more physically disturbed. Its surface looks torn apart and reconstructed from fragments that never belonged together. Vast canyons cut across the moon for hundreds of kilometers. Jagged cliffs rise above broken terrain. Some valleys reach depths of nearly 20 kilometers, far deeper than the Grand Canyon on Earth. The most dramatic feature is Verona Rupes. At approximately 20 kilometers high, it is the tallest known cliff in the solar system. Because Miranda's gravity is extraordinarily weak, an object dropped from its edge would take around 12 minutes to reach the ground below. Early scientists struggled to explain the moon at all. Some proposed that Miranda had been shattered completely by an ancient collision and later reassembled under its own gravity into a patchwork world. More recent models favor tidal heating, meaning internal warming caused by changing gravitational stresses during orbital interactions with Uranus and neighboring moons. But the surface still resists easy interpretation. Ariel presents a different mystery. Compared with many icy moons, its terrain appears surprisingly young. Smooth plains and long fault valleys suggest that liquid material may once have flowed outward from the interior, resurfacing large portions of the moon over time. Titania also carries signs of internal change. Huge fractures in canyon systems indicate that water beneath the crust may have frozen gradually, expanding as it solidified and splitting the outer layers apart through a process called freeze expansion. Then, in 2023, researchers revisited archival Voyager 2 data and identified signatures suggesting that several Uranian moons may still contain subsurface oceans beneath their icy crusts. Ariel, Umbriel, Titania, and Oberon all emerged as possible candidates, not frozen solid oceans, liquid ones, potentially maintained by internal heat trapped beneath kilometers of ice, warm enough, perhaps, for complex chemistry to persist in darkness no human instrument has ever directly explored. And all of that possibility came from re-examining data gathered during 6 passing hours in 1986. If you place Saturn and Uranus side by side in a telescope, Saturn would announce itself immediately. Its bright rings scatter sunlight so efficiently that even small backyard instruments can reveal them clearly from Earth. They appear broad, luminous, almost ornamental against the darkness of space. The rings of Uranus do the opposite. They hide. Uranus possesses 13 known rings, but they reflect only about 2 to 3% of the sunlight striking them. Coal reflects roughly the same amount. Some regions may be even darker. Against the blackness surrounding the planet, the rings become almost invisible unless sunlight hits them at precisely the right angle. Astronomers did not discover them by seeing them directly. On March 10, 1977, researchers were studying Uranus as it passed in front of a distant star. The technique is called stellar occultation, meaning astronomers observe how starlight changes when a foreground object moves across it. The goal was simple: measure the planet's diameter more accurately. But before Uranus crossed the starlight flickered unexpectedly. 5 brief dimming events appeared before the planet itself blocked the star. Then, after Uranus passed, the same dimming pattern repeated in reverse order. Something surrounding the planet had interrupted the light first. The rings revealed themselves through shadows. Today, stellar occultation remains one of the most important methods for studying distant planetary atmospheres and even some exoplanets orbiting other stars. Uranus's rings entered astronomy through a technique that would later become essential for exploring worlds far beyond the solar system. Voyager 2 confirmed the ring system during its 1986 flyby and identified two additional rings, bringing the total to 11 at the time. Later observations using the Hubble Space Telescope uncovered two more in 2003 and 2005. But their structure remains deeply unusual. Saturn's rings spread across hundreds of thousands of kilometers. Uranus's main epsilon ring narrows dramatically, ranging from roughly 20 to 100 kilometers wide, depending on location. The rings are also astonishingly thin, in some regions measuring only tens of meters vertically. Why do they not disperse? The answer involves shepherd moons, small moons whose gravity confines ring particles into narrow lanes. Cordelia and Ophelia orbit near the epsilon ring, continuously shaping it through gravitational interactions. Their influence acts almost like invisible boundaries, preventing the particles from drifting outward over time. Without those moons, the rings would slowly dissolve. The composition remains uncertain, though researchers suspect methane ice mixed with darker material dominates much of the structure. Over billions of years, radiation from space may have chemically altered the surface through a process called space weathering, where energetic particles gradually darken exposed ice and rock. But uncertainty still surrounds the deeper question. Why are Uranus's rings so dark while Saturn's remain brilliantly reflective? Why are they so narrow and confined instead of broad and diffuse? Scientists continue debating whether the difference comes from age, collisions between moons, or the composition of the original debris itself. The rings orbit quietly around Uranus, absorbing most of the sunlight that reaches them, almost refusing to be seen at all. The color of Uranus begins with methane. Without it, the planet would appear far less distinctive against the darkness of the outer solar system. The atmosphere consists of approximately 83% hydrogen, 15% helium, and around 2.3% methane, a small fraction with enormous visual consequences. Methane absorbs red wavelengths of sunlight. Blue and green light scatter back into space instead, giving Uranus its pale blue-green appearance. Neptune contains similar atmospheric ingredients, yet appears deeper and more saturated in color, a difference scientists still cannot fully explain despite decades of observation and modeling. The atmosphere keeps resisting simplicity. Far above the visible cloud tops lies the thermosphere, the uppermost atmospheric region where temperatures unexpectedly rise instead of falling. On Uranus, this layer can reach roughly 577 degrees Celsius. That temperature should not exist there. At Uranus's distance from the Sun, solar heating alone cannot account for such extreme warmth. Researchers call this discrepancy the Uranian energy crisis. Something inside the atmospheric system continues adding energy to the upper layers, but identifying the source has proven difficult. Several possibilities remain under investigation. Gravity waves, meaning ripples moving through the atmosphere caused by shifting pressure and density, may transport energy upward from deeper regions. Auroral heating could also contribute as charged particles interact with the upper atmosphere near magnetic field lines. Some studies point toward interactions between the ionosphere and the unstable magnetosphere surrounding the planet. The ionosphere is a region where solar radiation strips electrons from atoms, creating electrically charged particles. But no explanation fully matches the observations yet. Meanwhile, the winds race onward. Atmospheric currents on Uranus can exceed 900 kilometers per hour, faster than the strongest hurricanes ever recorded on Earth. These winds sweep through the upper layers continuously, redistributing gases and energy across the tilted planet. Yet, from far away, almost nothing appears to move. Jupiter displays enormous storms and turbulent cloud bands because internal heat drives dramatic temperature contrasts through the atmosphere. Uranus lacks much of that visible turbulence. The weak outward heat flow suppresses the large-scale convection patterns that create obvious storms on other giant planets. For years, Uranus appeared almost blank. Then, in 2006, the Hubble Space Telescope detected a bright storm system developing near the North Polar region. It was the first major atmospheric feature ever observed clearly on the planet. The timing mattered. Uranus had been approaching equinox, the period when sunlight reaches both hemispheres more evenly after decades of asymmetrical illumination. Gradually, the atmosphere became more active. Additional cloud structures emerged over subsequent years as northern summer approached, suggesting that seasonal sunlight eventually influences atmospheric circulation, though on timescales stretching across decades rather than days or months. And beneath those visible layers lies the coldest atmospheric boundary known anywhere in the solar system. The tropopause, meaning the transition region between the lower atmosphere and upper atmosphere, reaches approximately negative 224 degrees Celsius. Temperatures then begin rising again above it. Below that boundary, pressure increases rapidly. Within only a few hundred kilometers downward, the atmosphere thickens into dense, compressed fluid states where ordinary distinctions between gas and liquid gradually stop applying altogether. For most of human history, the planets of our solar system seemed sufficient to explain how worlds form. We had small, rocky planets close to the sun, giant gas planets farther out, and icy debris beyond them. The architecture felt complete. Then astronomers began finding planets around other stars. Thousands appeared. As telescopes improved, a pattern slowly emerged from the growing catalog of exoplanets. The most common large worlds in the galaxy did not resemble Jupiter. They did not resemble Saturn either. Again and again, astronomers detected planets falling into a size range closer to Uranus and Neptune. Ice giants seemed to dominate. In our own solar system, we divide planets into four broad categories: rocky planets, gas giants, ice giants, and dwarf planets. Yet, among these groups, ice giants remain the least explored and least understood, despite potentially representing the galaxy's most common planetary design. That realization changes the meaning of Uranus completely. It is no longer simply a strange outer planet orbiting far from Earth. It may instead be a standard example of how planetary systems naturally organize themselves across the Milky Way. If so, our understanding of one of the most abundant planetary types in existence currently rests on incomplete data gathered during a single flyby. And even the formation of Uranus itself remains difficult to explain. Modern planetary science relies heavily on the Nice model, developed in 2005. Named after the French city where it originated, the model attempts to reconstruct the early evolution of the solar system through gravitational interactions between the giant planets and the surrounding disk of debris. According to those calculations, Uranus and Neptune should not have formed where they currently orbit. The early solar nebula, meaning the cloud of gas and dust surrounding the young sun, would have been too sparse and too cold at those distances. Building planets of such size should have taken longer than the available lifetime of the nebula itself. So researchers proposed something more violent. Perhaps Uranus and Neptune formed much closer to the Sun before migrating outward through gravitational encounters with Jupiter and Saturn. In this scenario, the giant planets shifted positions dramatically during the solar system's infancy, scattering debris across enormous distances and destabilizing countless smaller bodies. That migration may have triggered the late heavy bombardment. This period, occurring roughly 4 billion years ago, involved intense asteroid and comet impacts across the inner solar system, including Earth and the Moon. Some scientists believe those collisions reshaped planetary surfaces, delivered water to young Earth, and altered the course of early planetary evolution permanently. If that picture is accurate, Uranus carries evidence of that ancient instability within its very structure. Its sideways rotation, trapped internal heat, unusual moons, and chaotic magnetic behavior may all trace back to gravitational events that transformed the entire solar system during its earliest era. So, studying Uranus is not a narrow scientific curiosity isolated at the edge of space. It is part of a much larger attempt to understand how planetary systems survive chaos, reorganize themselves, and eventually produce worlds capable of becoming homes. Long before the planets settled into their present arrangement, the solar system was crowded with unfinished worlds. Massive bodies crossed unstable orbits through clouds of gas, rock, and ice, colliding repeatedly as gravity sorted disorder into something more permanent. Nothing was calm yet. During the first 100 million years after the Sun formed, planetary embryos, meaning partially formed worlds, struck one another constantly. Some merged into larger planets, others shattered apart completely. The modern solar system emerged from that violence slowly, through impacts so energetic they reshaped entire worlds in single moments. Uranus may be one of the survivors. The leading explanation for its extreme tilt proposes a giant collision with a protoplanet roughly 1 to 3 times the mass of Earth. This was not a small object wandering accidentally through space. It was likely a fully differentiated world with its own internal layers, geology, and gravitational influence. The impact would have arrived at an angle, not directly head on, but obliquely, striking Uranus with enough rotational force to knock the planet permanently sideways without destroying it outright. That distinction matters because the outcome balanced on geometry. A slightly different trajectory could have changed everything. The energy released would have exceeded ordinary comprehension. Trillions of nuclear weapons would not approach the total force involved. Large portions of Uranus's outer atmosphere likely vaporized temporarily, expanding outward into space before cooling again over time. The internal structure of the planet would have been disrupted immediately, with shock waves moving through layers thousands of kilometers deep, and the effects may still be visible today. In 2018, researchers at Durham University modeled the collision in detail using computer simulations designed to reproduce Uranus's current structure. Their results showed that a giant impact could explain the sideways rotation successfully, but the simulation revealed something else as well. Material from the impactor appeared to spread into a thin shell around portions of Uranus's interior. That shell may now function as a thermal barrier, trapping heat deep inside the planet and contributing directly to the unusual coldness observed in the outer atmosphere. In other words, the same catastrophe that tilted Uranus may also have sealed away much of its primordial heat. The simulation uncovered another possibility, too. Had the impact occurred at a slightly different angle, Uranus could have lost most of its atmosphere entirely. The planet might have become little more than an exposed ice giant core drifting through the outer solar system without the thick gaseous layers we see today. The moons may also remember the collision. Debris ejected during the impact could have gathered into orbit around Uranus, gradually forming some of the moons over time. That origin might help explain their unusual orbital properties and the fractured appearance of places like Miranda. But the consequences may not have stopped there. Changing Uranus's mass distribution and orbital dynamics would also have altered the gravitational environment throughout the outer solar system. Small bodies, icy debris, and primitive comets could have shifted onto entirely new trajectories. Some of those objects may eventually have crossed Earth's path. If so, part of the water and organic material delivered to the early Earth may trace indirectly back to the event that broke Uranus billions of years ago. Time behaves differently on Uranus, not just because the planet orbits slowly, but because sunlight itself arrives there in patterns almost impossible to compare with life on Earth. Each Uranian season lasts approximately 21 Earth years. That timescale emerges from two facts working together: the planet's extreme tilt and its 84-year orbit around the Sunday. What results is the most prolonged and asymmetric seasonal cycle anywhere in the solar system. During solstice, one pole points almost directly toward the Sunday. For years, sunlight pours continuously across that hemisphere without interruption. The opposite pole remains turned entirely away, locked in darkness just as complete and just as long lasting. There is no sunrise waiting beyond the horizon, no dawn slowly approaching after winter, only night. But even this comparison understates the geometry involved. On Earth, polar summers still produce a moving sun, tracing low circles above the horizon. On Uranus during solstice, the sun can remain nearly fixed overhead for years at a time, barely shifting position in the sky while the planet continues rolling sideways through space. The equatorial regions experience stranger cycles still. There, sunrise and sunset occur rapidly during certain periods, then stretch into prolonged transitions unlike anything familiar on Earth. Because the rotational axis lies almost perpendicular to the orbital plane, ordinary assumptions about daylight collapse across much of the planet, and yet the atmosphere remains unexpectedly stable. Scientists predicted enormous temperature differences between illuminated and dark hemispheres. One side receives decades of solar heating, while the other loses energy continuously into space. Standard climate models suggested dramatic contrasts should develop across the globe, but observations showed something else. The atmosphere redistributes heat with remarkable efficiency, smoothing out thermal extremes far more effectively than expected. Even after decades of darkness, the cold hemisphere does not become radically colder than the sunlit side. Some mechanism, likely involving powerful atmospheric circulation and deep wind systems, moves energy across the planet in ways researchers still struggle to model accurately. This mystery became more apparent during Uranus's last northern equinox in 2007. An equinox occurs when both hemispheres receive roughly equal sunlight. For Uranus, that alignment happens only once every 42 years. Astronomers watched carefully as changing illumination transformed the atmosphere. Storm systems appeared. Bright cloud features emerged near the poles. Regions that once seemed almost motionless began displaying visible activity. The planet appeared to wake gradually. The next northern solstice will arrive in 2028. At that point, the North Pole will face the sun most directly, while the southern hemisphere enters another prolonged period of darkness, lasting roughly 2 decades. Human observation spans only fragments of these cycles. Modern telescopes have monitored Uranus carefully for less than a full seasonal transition. Much of what we know comes from brief intervals within atmospheric processes unfolding across generations. A single Uranian summer lasts longer than the recorded histories of most human civilizations. And somewhere beneath those slowly shifting seasons, the planet continues balancing heat and darkness according to rules we still do not fully understand. In 2023, scientists reopened data collected nearly 4 decades earlier. The information came from Voyager 2's plasma instruments, measurements recorded silently during the spacecraft's brief passage through the Uranian system in 1986. For 37 years, the signal meant nothing obvious. Then researchers noticed a pattern hidden inside the measurements, a disturbance consistent with Voyager, 2 passing through a plume of material erupting from one of Uranus's moons. The source was uncertain, though Ariel and Miranda emerged as the strongest candidates. That possibility changed the conversation immediately. Plumes in the outer solar system are not random phenomena. We already know them from Saturn's moon Enceladus and Jupiter's moon Europa, both of which eject water-rich material from beneath frozen crusts into surrounding space. Those moons are now considered among the most promising locations for extraterrestrial life anywhere in the solar system, because plumes imply hidden oceans. The process responsible is called tidal heating. As moons orbit giant planets, gravitational forces stretch and compress their interiors continuously. That repeated flexing generates heat through friction deep below the surface, warming internal layers enough to melt ice into liquid reservoirs trapped beneath frozen shells. The ocean remains sealed underneath. But fractures in the crust occasionally allow water vapor and particles to escape upward into space as jets or geysers. Spacecraft passing through those plumes can sample interior material indirectly without drilling through kilometers of ice. Cassini did exactly that at Enceladus. During 13 years studying Saturn, Cassini repeatedly flew through active plumes erupting from the moon's south polar region. It detected water vapor, salts, organic molecules, and chemical signatures associated with hydrothermal activity on the seafloor below. Those findings transformed planetary science. But Uranus received no equivalent mission. Instead, scientists returned to aging data archives from a flyby lasting only hours. Even so, the evidence continued growing. Another study, published in 2023, modeled heat transfer inside Uranus's larger moons and found that Ariel, Umbriel, Titania, and Oberon could plausibly maintain subsurface liquid oceans today. Not ancient oceans, present ones. The conditions required are surprisingly straightforward: liquid water, energy, and chemical ingredients capable of supporting complex reactions. Those ingredients may already exist inside multiple Uranian moons beneath layers of dark ice and fractured crust. And we have barely looked. The astrobiological argument for the Uranian system now rivals discussions surrounding Jupiter and Saturn in many respects. Yet Europa benefited from the Galileo mission. Enceladus received years of dedicated observations through Cassini. Uranus has nothing comparable, only fragments. This absence does not reflect scientific indifference. Planetary scientists have repeatedly argued for returning to Uranus because the potential rewards are enormous. But missions to the outer solar system demand decades of planning, billions of dollars, and political commitment extending across generations. So the moons continue orbiting in silence. Somewhere beneath their frozen surfaces, oceans may still move through darkness, untouched by sunlight, warmed slowly by gravity itself. If life exists there, it has remained hidden beneath ice, while human civilization debated whether the journey back was worth making at all. Seen from a distance, Miranda appears unremarkable. It is small, dim, and irregularly bright, one moon among many circling the tilted planet far beyond Saturn. Nothing about its size prepares you for what appears when the surface comes into focus. The landscape looks damaged. Miranda measures only 472 kilometers across, roughly comparable to the width of Arizona, yet its terrain ranks among the strangest ever photographed in the solar system. Vast canyons slice across ancient crust. Smooth plains sit abruptly beside heavily cratered regions. Long chevron-shaped grooves carve geometric patterns through the surface with almost unnatural precision. These formations are called coronae. A corona is a large oval structure thought to form when warmer material rises slowly from a moon's interior, pushing upward against colder outer layers. On Miranda, these upwellings appear to have distorted the crust repeatedly, creating enormous ridges and troughs unlike anything observed elsewhere. The moon looks assembled from incompatible pieces. Some regions appear ancient and battered by impacts billions of years old. Others seem comparatively young and resurfaced, as though geological activity erased earlier craters long after neighboring terrain stopped changing entirely. Then there is Verona Rupes. This immense cliff stretches approximately 20 kilometers from top to base, making it the tallest known cliff face in the solar system. It likely formed through faulting, meaning the crust fractured and shifted under intense internal stress. On Earth, cliffs collapse under gravity over geological time. Miranda's gravity is too weak for that process to occur efficiently, so the structure remains. Gravity on Miranda measures roughly 0.079 meters per second squared, around 123rd of Earth's surface gravity. If you stepped from the edge of Verona Rupes, you would not plunge downward rapidly. You would descend slowly for nearly 12 minutes before reaching the bottom. Even then, you would still strike the surface at roughly 100 meters per second. The contradictions continue everywhere scientists look. Early planetary researchers struggled to explain how such wildly different terrains could exist side by side on a body this small. One theory proposed that Miranda had once been shattered completely by a catastrophic impact. According to that idea, the fragments later reassembled under their own gravity, creating a patchwork moon built from broken remnants of itself. The hypothesis sounded extreme, but the surface encouraged extreme thinking. More recent models favor internal geological activity instead, especially periods of tidal heating caused by gravitational interactions with Uranus and neighboring moons. Different regions may have warmed, shifted, and cooled at different times, reshaping the crust unevenly across billions of years. Yet, even modern explanations feel incomplete when looking directly at the terrain. One planetary geologist described Miranda as resembling several unrelated moons compressed together into one object. The description remains difficult to improve upon, and we have seen surprisingly little of it. High-resolution imaging exists for only about 40% of Miranda's surface, all captured during Voyager 2's single flyby in 1986. The remaining majority still waits unseen in darkness, carrying landscapes no human instrument has ever observed. The rings of Uranus appear delicate, almost motionless from afar. Thin bands circle the planet quietly in darkness, holding their shapes with improbable precision over immense spans of time. But left alone, they would not survive. Every ring particle follows its own orbit around Uranus, moving at slightly different speeds depending on distance from the planet. Over millions of years, those differences should gradually spread the material outward until the rings dissolve into diffuse clouds too faint to recognize. Yet the rings remain narrow. That persistence reveals an invisible system of control operating continuously around the planet. Small moons orbit beside the rings, shaping them through gravity with extraordinary precision. Astronomers call them shepherd moons because their influence confines ring particles into sharply defined lanes. The most famous pair are Cordelia and Ophelia. Both moons measure less than 50 kilometers across and orbit on opposite sides of the Epsilon ring, the brightest and outermost major ring of Uranus. Their gravitational pull creates a process called resonance, meaning repeated orbital interactions that stabilize particle motion over time. One moon pulls inward, the other pulls outward. Together, they prevent the ring from dispersing. What makes this especially remarkable is that scientists predicted such moons before ever seeing them directly. Mathematical models of orbital mechanics suggested narrow rings could not persist naturally without gravitational confinement nearby. Then Voyager 2 arrived. Its observations in 1986 confirmed the existence of shepherd moons exactly where theory predicted they should be. The discovery became one of the clearest demonstrations that orbital dynamics, the mathematics governing gravitational motion, could accurately describe structures billions of kilometers away. And the moons themselves are strange objects. They are dark, irregular, and heavily cratered, absorbing most of the sunlight, reaching them just as the rings do. Their shapes suggest bodies too small for gravity to pull into spheres, leaving them uneven and distorted, like ancient fragments drifting close to the planet. Some orbit dangerously near the Roche limit. The Roche limit is the distance where tidal forces from a planet become strong enough to tear apart a solid object held together only by its own gravity. Inside that boundary, moons can fracture gradually under gravitational stress until they disintegrate into debris. Cordelia orbits roughly 49,770 kilometers from Uranus's center, deep within this unstable region where rings and moons exist in delicate balance. The system continues evolving even now. Over hundreds of millions of years, some inner moons may spiral inward or experience increasing tidal disruption. If that happens, they could break apart and contribute fresh material to the rings surrounding Uranus. The rings we observe today are temporary structures. They were not always arranged this way, and eventually they will change again. Their material may originate from moons that no longer exist, bodies shattered long ago through collisions or tidal destruction until only fragments remained in orbit. So the ring system becomes something more than decoration. It may be a graveyard. Every narrow band circling Uranus could contain the remnants of ancient worlds reduced to dust, ice, and darkened debris, still orbiting the planet that ultimately pulled them apart. For decades, planetary scientists have agreed on something surprisingly rare. Uranus deserves a dedicated mission. Not eventually, not as a distant possibility, as a priority. The recommendations exist in writing. Every 10 years, the National Academies of Sciences publishes the Planetary Science Decadal Survey, a document that guides NASA's major exploration priorities. These surveys shape which missions receive long-term support, funding attention, and engineering development across the following decade. In 2011, the survey ranked a Uranus orbiter and atmospheric probe as the third highest planetary priority. Then the ranking climbed higher, The 2023 Decadal Survey placed a Uranus orbiter and probe mission at the very top of the list, the highest recommendation possible for planetary science. The scientific case had become overwhelming. Researchers wanted long-term atmospheric observations, detailed mapping of the magnetic field, direct sampling of the atmosphere, and close flybys of moons that might conceal oceans beneath their frozen crusts. Still, no mission has been approved as of 2026. The obstacle is not indifference, it is scale. A Uranus mission would require roughly $4.2 billion across development, launch, operations, and decades of mission support. That figure places it in the same category as Cassini, the spacecraft that orbited Saturn for 13 years and permanently transformed our understanding of its rings, moons, and atmosphere. The technical demands are equally severe. A spacecraft traveling to Uranus must survive years in deep space, operate far beyond the warmth of the inner solar system, and communicate across billions of kilometers with significant signal delays. Every system must function reliably after more than a decade in transit before scientific observations even begin. Timing matters too. The most efficient launch opportunity opens in 2031, when Jupiter's position will allow a gravity assist maneuver. A gravity assist uses a planet's motion and gravity to accelerate a spacecraft without additional fuel expenditure, dramatically shortening travel time to distant targets. Miss that window, and the journey grows longer. If funding began immediately and development proceeded without major delays, a spacecraft could potentially reach Uranus sometime during the early 2040s. The scientists designing the mission today may spend half their professional lives waiting for the first data to arrive. Some already have. Entire generations of researchers built careers studying Uranus using only Voyager, two observations, Hubble imagery, and measurements from ground-based telescopes. Many devoted decades to understanding a planet glimpsed closely for just 6 hours. And still they continue arguing for return missions. Because the unanswered questions remain unusually fundamental. Scientists are not debating small details or minor refinements. They still do not know how Uranus traps heat, how its magnetic field evolves over seasons, whether several moons contain oceans, or how the planet formed in the first place. But large missions compete against one another constantly. Mars exploration, lunar programs, asteroid missions, telescopes, and outer planet projects all draw from finite budgets and limited launch capacity. Building a spacecraft capable of surviving the outer solar system requires years of engineering, political support, and institutional patience. By the time the first new images arrive from Uranus again, entire careers will already have passed waiting for them. Imagine remaining at Uranus instead of rushing past it. Not 6 hours of observation collected during a single flyby, but years spent circling the planet continuously, watching storms evolve, magnetic fields shift, and distant moons rotate beneath changing sunlight. That is the purpose of the proposed Uranus orbiter and probe mission. Unlike Voyager 2, the spacecraft would not simply pass through the system. It would break into orbit around Uranus and remain there for at least 4 years, conducting repeated observations across seasons, hemispheres, and magnetic conditions impossible to study during a brief encounter. And part of the mission would fall directly into the planet itself. A separate atmospheric probe would detach from the orbiter before arrival and descend into Uranus's atmosphere, transmitting measurements for roughly 60 to 90 minutes before pressure and temperature destroyed it completely. That short descent could change planetary science permanently. NASA used a similar strategy at Jupiter in 1995 when the Galileo probe entered the Jovian atmosphere. During only 57 minutes of transmission, it transformed scientific understanding of Jupiter's chemistry, cloud structure, and atmospheric dynamics. No spacecraft has ever performed that experiment at an ice giant. For the first time, scientists could directly measure temperature, pressure, wind speed, and atmospheric composition beneath Uranus's visible cloud layers rather than inferring conditions remotely from telescopes. The probe would descend into regions no human instrument has ever sampled anywhere in the outer solar system. Meanwhile, the orbiter would begin surveying the moons. Close flybys of Miranda, Ariel, Umbriel, Titania, and Oberon would allow detailed mapping of their surfaces and interiors. Instruments could search for hidden oceans using magnetic induction, a method that detects electrically conductive liquid beneath ice through interactions with changing magnetic fields. Gravitational mapping would reveal internal density structures. High-resolution imaging could examine fractures, canyons, plume sources, and resurfaced terrain in extraordinary detail. Much of Miranda's unseen hemisphere could finally come into view for the first time since the moon was discovered. The spacecraft would also carry an advanced magnetometer. A magnetometer measures the strength and orientation of magnetic fields surrounding planets and moons. With long-term orbital observations, scientists could finally determine whether Uranus's magnetic field truly shifts, weakens, or temporarily collapses during seasonal changes, as some models predict. The timing matters because Uranus approaches northern solstice in 2028. A mission arriving during the following decades could observe how the atmosphere and magnetosphere respond as sunlight geometry changes across the planet. For Uranus, seasonal transformations unfold slowly enough that continuous observation becomes essential, and the technology already exists. Scientific teams have spent years refining instruments and mission architectures through repeated decadal survey cycles. The challenge is no longer whether engineers can build the spacecraft, they can. The deeper question is whether humanity chooses to send it, because the scientific return would extend far beyond Uranus itself. Every ice giant discovered orbiting another star could be interpreted more accurately through direct comparisons with in situ measurements gathered inside our own solar system. In that sense, the mission would not merely explore Uranus. It would become the reference point for understanding one of the most common planetary types in the galaxy. On Earth, auroras follow rules you can visualize easily. Charged particles from the solar wind travel along magnetic field lines toward the poles, where they collide with gases high in the atmosphere and release light across the sky. The geometry is orderly. Magnetic north lies close to geographic north, so auroras gather predictably around polar regions in glowing circular bands. Even Jupiter and Saturn, despite their enormous differences from Earth, produce auroras following broadly similar magnetic logic. Uranus does not. Its magnetic field tilts roughly 59 degrees away from the planet's rotational axis and emerges from a point significantly offset from the center. Instead of surrounding the planet symmetrically, the field twists through space unevenly as Uranus rotates sideways through its orbit. The auroras follow that instability. Rather than appearing near geographic poles, Uranian auroras emerge in scattered patches across unexpected regions of the atmosphere. They drift, distort, and reorient themselves according to the tumbling magnetic field instead of the planet beneath them. For a long time, no one observed them clearly. Then, in 2011, the Hubble Space Telescope captured the first confirmed images of auroral emissions on Uranus. The observations revealed bright ultraviolet arcs glowing across the atmosphere far from where conventional auroras should appear. Ultraviolet light lies beyond human vision, to instruments sensitive enough to detect it. However, the emissions traced irregular, luminous structures moving across the planet in patterns unlike those seen anywhere else in the solar system, and they do not remain fixed. Because the magnetic field itself rotates in a corkscrew configuration, the auroras drift with it across the atmosphere. In a sense, the light show belongs to the magnetic field rather than the planet's geography. The distinction matters because Uranus's magnetosphere, meaning the region dominated by its magnetic influence, may itself change dramatically over seasonal timescales. Some simulations suggest the field occasionally weakens or partially collapses. If that happens, the auroras could temporarily disappear altogether before reforming later as magnetic structure reestablishes itself. During those periods, the upper atmosphere would become more exposed to charged particles streaming outward from the sunday. That interaction slowly removes material from the planet. Scientists call the process atmospheric escape, where atoms and molecules gain enough energy to leave the atmosphere permanently and drift into space. On Uranus, hydrogen appears to escape gradually through interactions between the ionosphere and the solar wind. The ionosphere is the electrically charged upper region of the atmosphere, shaped by radiation and magnetic forces. Researchers still do not know how rapidly Uranus loses atmospheric material because observations remain too limited. Measuring escape rates requires long-term monitoring across different solar conditions and seasonal configurations, something no spacecraft has yet performed. So the auroras remain fragments of a larger mystery. They flicker irregularly at the edge of the solar system, tracing invisible magnetic structures no other planet produces in quite the same way. Their shifting light reveals the shape of forces operating deep inside Uranus itself, forces distorted, displaced, and possibly interrupted entirely. Very few human instruments have ever watched them closely, yet every auroral pulse carries information outward through the darkness, a visible expression of the strange magnetic architecture hidden beneath the planet's pale atmosphere. Tonight, when you look upward, almost every visible star likely hosts planets of its own. For most of human history, those worlds existed only as speculation. Now they fill astronomical catalogs by the thousands. As of 2026, scientists have confirmed more than 5,700 exoplanets orbiting distant stars. Space telescopes such as Kepler Space Telescope and Transiting Exoplanet Survey Satellite, along with observatories scattered across Earth's surface, transformed planets beyond the solar system from theory into measured reality. Patterns quickly emerged. The galaxy appears crowded with worlds unlike anything orbiting our Sunday. The most common large planets discovered so far fall between Earth and Neptune in size, a category astronomers call sub-Neptunes or mini-Neptunes. These planets typically measure between 2 and 4 Earth radii and often possess thick atmospheres, rich in hydrogen, methane, and volatile compounds. We have no direct example nearby. Earth is too small. Neptune is too distant and massive. So, when astronomers attempt to understand these common alien planets, they turn toward the closest analogs available, Uranus and Neptune, the least explored major planets in our own system. That limitation shapes modern astronomy more than most people realize. When telescopes detect a planet roughly 3 or 4 times wider than Earth and perhaps 10 or 15 times its mass, researchers infer an internal structure resembling an ice giant. But those conclusions rely heavily on atmospheric models, thermal dynamics, and magnetic theories derived from Uranus. And those theories remain incomplete. The James Webb Space Telescope has already begun analyzing the atmospheres of several sub-Neptune exoplanets in remarkable detail. By studying how starlight filters through alien atmospheres during planetary transits, astronomers can identify molecules such as water vapor, carbon dioxide, methane, and hydrogen sulfide. Yet, interpretation depends on comparison. To understand distant spectra, researchers need accurate models describing how ice giant atmospheres behave under different temperatures, pressures, and stellar conditions. Right now, many of those models still trace back to a single spacecraft flyby lasting only 6 hours in 1986. That is a remarkably thin foundation. In a very real sense, Uranus functions as a Rosetta Stone for planetary science, a nearby translation key for interpreting thousands of distant worlds we will never physically reach. But Uranus may also be more typical than we once believed. Several exoplanets discovered during the past decade appear to possess extreme axial tilts comparable to Uranus. That suggests giant collisions capable of knocking planets sideways could be common during planetary formation. Entire solar systems may experience violent migrations and impacts as ordinary stages of evolution rather than rare catastrophes. If so, Uranus stops looking broken. Instead, it begins looking familiar. Perhaps the strange planet rolling silently beyond Saturn represents the dominant planetary architecture of the Milky Way, while our orderly inner solar system is the unusual exception. Understanding Uranus, therefore, reaches far beyond one distant world. It shapes how we interpret the broader structure of planets throughout the observable universe, including worlds whose light has traveled hundreds of years before reaching us tonight. Long before spacecraft reached Uranus, language arrived there first. Names crossed the dark centuries ahead of machines, carrying fragments of theater, poetry, and human imagination into the cold outer system. Every confirmed major moon of Uranus draws its name from English literature, specifically the works of William Shakespeare and Alexander Pope. No other planetary moon system follows this tradition. Jupiter's moons borrow from mythology. Saturn favors titans and giants. But Uranus became something stranger, a distant archive of fictional characters orbiting beneath frozen sunlight. The naming tradition began with John Herschel, son of Uranus's discoverer. In the 19th century, he proposed literary names rather than mythological ones, and the astronomical community accepted the idea. Over time, the Uranian system slowly filled with figures from plays and poems written centuries earlier on Earth. The five largest moons carry some of the most recognizable names. Titania and Oberon come from Shakespeare's A Midsummer Night's Dream, rulers of a hidden fairy kingdom moving invisibly through forests and moonlight. Ariel and Miranda come from The Tempest, a story shaped by storms, isolation, and uncertain boundaries between knowledge and illusion. Miranda feels particularly fitting. In Shakespeare's play, Miranda grows up isolated from the wider world, living on a remote island shaped by forces she only partly understands. The moon bearing her name sits billions of kilometers away, scarred by cliffs, broken terrain, and immense canyons we have barely mapped. A literary coincidence emerged across centuries without planning it. Both Mirandas exist at the edge of familiarity. Umbriel comes from Pope's The Rape of the Lock, where Umbriel appears as a gloomy spirit associated with shadow and melancholy. Astronomers later discovered that Umbriel the moon is the darkest of Uranus's major satellites, reflecting only around 16% of incoming sunlight. Even the smaller moons continue the pattern. Voyager 2 revealed moons named Cordelia, Ophelia, and Bianca, all drawn from Shakespearean drama. More distant, irregular moons, discovered through ground telescopes, later received names such as Caliban, Sycorax, Prospero, and Setebos, figures connected again to the Tempest. That repeated return to one play feels strangely appropriate. It is a story about exile, unstable power, and encounters with the unknown. But the naming system became more than a cataloging method. Without deliberate intention, Uranus accumulated the most culturally layered nomenclature in the solar system beyond Earth. Literature now circles an ice giant in permanent orbit. Human stories drift around a planet defined by mystery, darkness, and distance. At the boundary of explored space, scientific observation and imagination remain quietly intertwined, each giving shape to places the other cannot fully reach alone. Some planets seem restless. Jupiter turns rapidly beneath shifting storms. Mars races through recognizable seasons within a human lifetime. But Uranus moves with extraordinary patience, carrying its weather, sunlight, and shadows through cycles longer than civilizations. One complete orbit around the Sun takes Uranus approximately 84.01 Earth years. That single number changes the meaning of nearly everything we observe there. Since William Herschel discovered Uranus in 1781, the planet has completed fewer than 3 full journeys around the Sunday. Humanity has not yet watched Uranus experience 3 complete years. That realization compresses history in unsettling ways. A person born during the discovery year, who survived to age 84, would have witnessed Uranus return to exactly the same orbital position only once. Entire human lives fit inside single Uranian seasons. The last time Uranus occupied the same region of space it does tonight, the modern world barely existed in recognizable form. The American Civil War had not begun. Charles Darwin had not yet published on the origin of species. The first transatlantic telegraph cable still lay in the future. Uranus completed its second observed orbit in 1865. That same year, the Civil War ended and Abraham Lincoln was assassinated. The planet continued silently through darkness while nations rose, industrialized, and transformed beneath it. Its third observed orbit will complete in 2033. For planetary scientists, this slow motion creates unusual problems. Studying seasonal cycles on Earth requires years. Studying them on Saturn requires decades. Studying Uranus properly demands observations across centuries. Modern astronomy has existed for only a fraction of 1 Uranian year. Even our best telescopes arrived late. Detailed planetary imaging through instruments like the Hubble Space Telescope covers only a narrow slice of Uranus's orbital history. When Hubble observed storms emerging near the 2007 equinox, astronomers realized they were witnessing the first clearly documented seasonal atmospheric transition ever recorded on the planet. No comparable observations existed for the previous equinox in 1923. The telescopes of that era lacked sufficient resolution. The equinox before that occurred in 1839, decades before photography itself became scientifically practical. So each new season on Uranus arrives almost undocumented. Every storm, cloud band, aurora, and atmospheric shift becomes historically unique because no earlier scientific generation possessed the tools necessary to observe it properly. Even today, researchers often compare current images not with centuries of detailed archives, but with sparse snapshots scattered across incomplete records. But the slowness of Uranus affects more than science. Human institutions rarely sustain uninterrupted focus across 80-year cycles. Careers end. Funding priorities shift. Space programs evolve through political eras far shorter than a Uranian season. The planet exists on timescales larger than ordinary human planning, and that distance in time has become one of the quiet reasons Uranus remains so deeply mysterious to us still. Out near Uranus, space is not silent. The vacuum carries no ordinary sound, no moving air, no echoing vibration. But invisible electrical activity fills the darkness continuously, flowing through magnetic fields and charged particles like weather passing through another dimension. When Voyager 2 crossed the Uranian system in 1986, it carried instruments capable of detecting radio emissions, electromagnetic waves generated through interactions between the solar wind and planetary magnetospheres. Those emissions cannot be heard directly by human ears. Their frequencies sit far outside natural hearing ranges, but scientists can shift the signals into audible frequencies, transforming plasma activity into sound. Each giant planet produces a distinct electromagnetic voice. Jupiter sounds immense and violent, full of roaring bursts and descending whistles created by its enormous magnetic field, trapping charged particles in vast radiation belts. Saturn produces slower rhythmic pulses, repeating with mechanical regularity, almost like a distant heartbeat echoing through static. But Uranus sounds different immediately. Its emissions arrive as scattered whistles, abrupt clicks, unstable hisses, and drifting tones that seem unable to settle into stable patterns. The recordings feel irregular even before you understand the underlying physics. That irregularity matters. These signals, known as plasma waves, contain information about charged particle density, temperature, magnetic structure, and motion within the magnetosphere surrounding the planet. The strange audio reflects the geometry of Uranus itself. Its magnetic field does not rotate cleanly around the planet's axis. Instead, the field tilts dramatically and tumbles outward in a corkscrew pattern as Uranus spins. Charged particles become trapped inside that shifting magnetic structure, generating radio emissions that twist and fluctuate constantly. The sounds inherit the instability of the field that creates them. Scientists analyzing Voyager 2's plasma recordings found that Uranus behaved unlike any previously observed planetary magnetosphere. Regions of electrical activity appeared displaced, asymmetric, and constantly changing orientation relative to the solar wind flowing outward from the sunday. Even the rhythm feels uncertain. NASA later converted portions of those emissions into publicly available audio files. People listening for the first time often describe them as eerie or unsettling, not because the sounds were designed dramatically, but because the underlying planetary system genuinely behaves in unusual ways. The recordings themselves remain brief. Voyager 2 spent only hours near Uranus during closest approach, gathering a tiny sample from an environment that changes seasonally across decades. Every whistle and burst preserved in those archives comes from a spacecraft moving rapidly through a magnetic system. No human instrument has revisited since. But the sounds carry something strangely intimate. Light from Uranus shows us atmosphere and color. Gravity reveals mass and orbital motion. These plasma emissions reveal behavior, instability, and motion hidden within invisible magnetic architecture. We are not hearing weather or wind. We are hearing electrical structure translated into human perception. And the translated voice of Uranus sounds scattered, restless, and unresolved, as though the planet's magnetic interior never fully recovered from whatever ancient event pushed the entire world sideways long ago. Deep beneath Uranus's pale atmosphere, heat almost certainly still survives. The strange part is not that warmth exists there. The strange part is that we barely see any trace of it escaping. Every major planet began violently. During formation, countless collisions converted motion into thermal energy, while gravity compressed, growing worlds into denser forms. Young planets glowed with retained heat, their interiors churning from the energy of creation itself. Most giant planets still radiate that ancient warmth outward today. Jupiter emits roughly 1.67 times more energy than it receives from sunlight. Saturn radiates even more relative excess heat, and Neptune releases over 2.5 times the solar energy falling onto it. Their interiors continue slowly cooling after 4.5 billion years. But Uranus behaves differently. Measurements gathered since the Voyager 2 encounter suggest Uranus emits almost no detectable excess internal heat at all. In energy terms, it exists close to thermal equilibrium, with the weak sunlight reaching it across billions of kilometers. That result should not happen naturally. An ice giant of Uranus's size should still retain significant primordial heat, especially deep within its compressed interior. Yet the cloud tops remain extraordinarily cold, while the atmosphere above shows little evidence of strong upward thermal flow. Somewhere, the energy became trapped. Planetary scientists increasingly suspect the answer connects directly to the ancient impact that knocked Uranus sideways early in solar system history. Simulations suggest the collision may have rearranged the planet's internal layers into unusually stable configurations, preventing convection from carrying heat upward efficiently. Convection is heat transfer through moving fluid. On Earth, boiling water circulates because warm material rises while cooler material sinks. Giant planets typically transport internal heat the same way. But Uranus may contain a barrier. Researchers propose that layers rich in superionic water, ammonia, and methane became organized after the collision into thermally stable strata that resist mixing. Instead of circulating freely, heat became sealed beneath insulating layers thousands of kilometers thick. If this interpretation is correct, Uranus did not lose all its primordial energy. It imprisoned it. Models still estimate interior temperatures reaching several thousand degrees Kelvin, hot enough for exotic chemistry and electrically conductive fluids to persist deep below the visible atmosphere. Yet almost none of that warmth reaches the upper cloud decks we observe remotely from Earth. The temperature contrast may be among the largest anywhere in the solar system. At the visible cloud tops, temperatures plunge near negative 224 degrees Celsius. Far below, pressure climbs into millions of atmospheres, while temperatures rise high enough to melt rock and transform water into states impossible under Earth conditions. Between those regions sits an immense volume of poorly understood fluid, acting almost like planetary insulation. But the mystery remains frustratingly incomplete because every conclusion still depends on indirect measurements, computer simulations, and 6 hours of flyby data collected decades ago. No spacecraft has ever descended into Uranus's atmosphere to measure these thermal layers directly. So the coldness we observe may not represent emptiness or inactivity at all. It may represent containment, a vast planetary shell holding ancient heat beneath its surface for 4 billion years, unable to release the consequences of its own catastrophic formation. Far beneath the frozen crusts of Uranus's larger moons, darkness may conceal oceans that have existed longer than complex life on Earth. No sunlight reaches those waters. No telescope can see through the ice above them. Yet modern planetary science can no longer dismiss their existence. No serious researcher currently claims that life has been discovered anywhere in the Uranian system. The evidence simply does not exist. But the more difficult scientific question is whether life there can honestly be excluded. For Uranus itself, the answer appears straightforward. The planet's atmosphere is extraordinarily hostile to biology as we understand it. Temperatures plunge far below the freezing point of water, while pressures rise rapidly with depth into crushing extremes. Methane, hydrogen, and ammonia dominate the chemistry. Stable liquid water environments, suitable for known biochemistry, appear highly unlikely within the atmospheric layers accessible to study. But the moons change the conversation entirely. Evidence gathered from reanalyzed Voyager 2 data, combined with modern thermal models, suggests that Ariel, Umbriel, Titania, and Oberon may contain subsurface oceans beneath their icy crusts. The evidence remains indirect, but multiple peer-reviewed studies now treat the possibility seriously rather than speculatively. That shift matters. On Earth, life persists almost everywhere liquid water exists. Microorganisms survive beneath Antarctic ice sheets, kilometers thick. Entire ecosystems thrive around hydrothermal vents at the bottom of the ocean where sunlight never penetrates. Some organisms tolerate extreme acidity, intense pressure, or temperatures once thought incompatible with biology. Life repeatedly demonstrates adaptability beyond earlier expectations. The environments potentially existing inside Uranian moons are not fundamentally alien to known habitability models. Scientists envision liquid water reservoirs insulated beneath thick ice layers, heated internally through tidal flexing caused by gravitational interactions with Uranus and neighboring moons. Tidal heating means gravitational forces repeatedly squeeze and stretch a moon's interior, generating frictional warmth over immense timescales. The same mechanism powers subsurface oceans on Europa and Enceladus elsewhere in the solar system. Chemical ingredients also appear available: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The 6 primary elements associated with terrestrial biology exist throughout the outer solar system in various compounds and ices. Rocky seafloors interacting with liquid water could potentially create chemically active environments similar to those surrounding Earth's hydrothermal systems. None of this demonstrates that life exists there. It simply means the known requirements for life are not obviously absent. That distinction defines much of modern astrobiology. Scientists no longer ask only where life certainly exists. Increasingly, they ask where biology remains chemically and physically plausible. But our ignorance surrounding Uranus remains unusually self-imposed. Europa received dedicated missions. Saturn's moon Enceladus benefited from 13 years of Cassini observations. The Uranian system received 6 hours during a flyby in 1986, and then decades of silence afterward. So the most unsettling possibility may not be that life survives beneath those distant icy crusts. It may be that conditions suitable for life have existed there for billions of years, while humanity, fully aware of the possibility, simply chose not to return and look more closely. Distance in the outer solar system stops behaving like ordinary distance. On Earth, you measure separation in roads, oceans, and flights. Around Uranus, separation becomes something quieter. Vast stretches of nearly perfect vacuum where light itself requires hours to cross the emptiness. Uranus orbits the Sun at an average distance of 2.87 billion kilometers. The number is so large that the human mind struggles to attach meaning to it. Even radio signals, moving at light speed, require approximately 2 hours and 40 minutes to travel one way between Earth and the planet. At the speed of a commercial aircraft, roughly 900 kilometers per hour, reaching Uranus would take more than 3.5 centuries. Entire civilizations could rise and disappear during the journey. Voyager 2 made the crossing in 9 years. It launched in 1977, accelerated outward through carefully timed gravity assists, and arrived at Uranus in 1986, already moving faster than 35,000 kilometers per hour. Even then, the voyage consumed nearly a decade simply to reach one stop in the outer solar system. But once you arrive, the isolation deepens. From Uranus, the sun no longer dominates the sky the way it does from Earth. It shrinks into an intensely brilliant point, surrounded by countless other stars, still brighter than anything nearby, certainly, but no longer overwhelming, no longer close. Sunlight there is approximately 400 times dimmer than on Earth. If you could somehow stand within the upper atmosphere and look outward through the haze, the illumination would resemble a heavily overcast afternoon rather than daylight as we know it. Everything becomes muted. The moons orbit silently through that dimness. 28 known worlds of rock and ice circling a planet tipped onto its side. Ariel, Titania, Oberon, Miranda. Their surfaces receive weak sunlight that takes nearly 3 hours to arrive from the distant sun, touching landscapes no human eyes have directly observed since Voyager passed by. The emptiness between planets also changes scale completely in the outer system. Between Earth and Mars, distances still feel navigable. Between Saturn and Uranus, space begins to feel less like geography and more like abandonment. Billions of kilometers contain almost nothing at all. A few particles, faint magnetic fields, thin streams of solar wind, mostly silence. Uranus drifts through that silence continuously. Its magnetic field twists and tumbles through space. Its rings circle in darkness. Deep inside, ancient heat remains trapped beneath layers of exotic fluid, while the cloud tops stay colder than any other planetary atmosphere yet measured. And through all of it, the planet simply continues. No human being alive today will ever stand near Uranus. No crewed mission exists, even as a serious proposal. The distances remain too large, the travel times too long, the engineering demands too unforgiving. But Uranus does not require witnesses to exist. It rolls slowly onward through the dark, patient and unchanged, exactly where it has been for billions of years. Science is often described as a collection of answers, but for the people who study planets, it feels more like mapping the edges of fog. Some mysteries are clear enough to describe precisely. Others exist beyond the edge of measurement, where even the shape of the question remains uncertain. Planetary scientists separate these unknowns into categories. There are open questions, problems where evidence exists but certainty does not. Then there are deeper unknowns, places where the available data is so thin that we cannot yet tell what information is missing. Uranus occupies both territories at once. The list of open questions alone is remarkably large. Why does Uranus emit almost no detectable internal heat, while Neptune, farther from the Sun, radiates substantial energy into space? What is the exact structure of the interior beneath the atmosphere? Does superionic water truly dominate the middle layers, conducting electricity through crystalline oxygen lattices deep inside the planet? No confirmed answer exists. Scientists also continue debating the precise origin of the axial tilt. A single impact remains the leading explanation, but some simulations now favor multiple collisions occurring over extended periods during the early solar system. The observed geometry may contain traces of several catastrophes layered together. Then there is the magnetic field. We know it tilts dramatically away from the rotational axis. We know it is offset from the planet's center, but we still do not know whether the field partially collapses during seasonal changes or how the magnetosphere behaves during intense solar activity, because no spacecraft has remained long enough to observe those transitions directly. The moons deepen the uncertainty further. Do Ariel, Umbriel, Titania, and Oberon contain subsurface oceans? Are the suspected plumes real eruptions of water and volatile material, or were they temporary plasma effects recorded during Voyager 2's brief passage? What chemistry exists beneath those frozen crusts? We cannot yet say. But beyond those specific mysteries lies another category entirely, questions not yet formulated. What would happen during the first hour of an atmospheric descent probe entering Uranus? Would the measured composition match existing models, or immediately overturn them the way the Galileo probe transformed our understanding of Jupiter in 1995? What does the unseen 60% of Miranda actually look like? Voyager photographed only one hemisphere clearly during its flyby. Entire canyon systems, fault networks, or geological formations may still wait on the hidden side of the moon, completely unknown to us. This imbalance between scale and understanding is scientifically unusual. Uranus is not a distant exoplanet glimpsed through indirect measurements. It is a major planet in our own solar system, larger than Earth by a factor of 4, orbiting well within the reach of robotic exploration. Yet in certain foundational ways, we understand some Kuiper Belt objects more clearly because they were observed recently with modern instruments. But perhaps that is what makes Uranus so compelling. In the language of planetary science, it is not a solved world with a few remaining puzzles. It is a frontier still covered by a thin layer of first observations, waiting for an entirely deeper level of understanding beneath. Try to picture a world where most of the important details remain hidden, not hidden because they are impossible to reach, but because we simply have not returned long enough to look carefully. Uranus exists inside that strange category of scientific knowledge, familiar in outline, unknown in substance. Even now, enormous portions of the system remain completely unseen. Roughly 60% of Miranda's surface has never been imaged at high resolution by any spacecraft. Everything beyond the hemisphere captured during Voyager 2's 1986 flyby remains largely invisible to us. There may be larger cliffs there, vast canyon systems, entire geological regions unlike anything already photographed. We do not know. The interiors of the 5 major moons are even more mysterious. Ariel, Umbriel, Titania, Oberon, Miranda. We can estimate densities and surface compositions from reflected light and orbital motion, but beneath the crusts, direct knowledge ends almost immediately. No spacecraft has mapped their internal structures through gravity measurements or magnetic induction. The suspected oceans beneath several of those moons remain theoretical spaces hidden under kilometers of ice. The same limitation extends to Uranus itself. We have never directly measured the chemistry of the deep atmosphere below the visible cloud tops. Telescopes can analyze reflected light from upper layers, identifying methane, hydrogen, and helium. But farther down, where pressure rises into thousands of atmospheres, the composition becomes uncertain. No probe has ever descended there. We have also never sampled a single particle from the rings. Every conclusion about their composition comes indirectly through spectroscopy, the analysis of reflected wavelengths. The dark material circling Uranus may contain irradiated methane, ice, carbon compounds, silicates, or mixtures still poorly understood. No human instrument has touched it. Then there is time itself. The full behavior of Uranus across an entire seasonal cycle has never been observed with modern equipment. Voyager arrived near southern solstice when one hemisphere faced decades of darkness. Since then, telescopes have watched the atmosphere slowly awaken, approaching equinox, producing storms absent during the flyby era. But we have still never monitored the planet continuously through a complete transition from equinox to solstice and back again. Critical phases remain missing. The magnetic field presents the same problem. Scientists suspect seasonal restructuring, perhaps even partial collapse and reformation, driven by the planet's bizarre geometry. But confirming that idea requires decades of continuous observation. We possess one snapshot from 1986. That is all. This creates a scientifically extraordinary situation. Uranus is not a distant object at the edge of the galaxy. It is a major planet in our own solar system, larger than Earth, surrounded by moons that may contain oceans, rings we have never sampled, and atmospheric layers we have never entered. Yet the catalog of what we have not seen remains longer than the catalog of what we have. In the most literal sense possible, Uranus is the least understood large world in the entire known solar system. Long before we can answer the mysteries of Uranus, another question waits underneath them. Not a technical question, not a mathematical one, a human question. What does it mean to know a world exists? To suspect it may contain hidden oceans and unfamiliar chemistry, and then to leave it almost entirely unexplored for decades? The answer is not simple. Space exploration has always involved compromise. Every mission approved means another mission delayed. Budgets are finite. Launch windows close. Engineering teams age through development cycles that last half a career. The scientists advocating for Uranus are not competing against ignorance or indifference. They are competing against other important worlds. Mars demands attention. Europa does. Titan does. Each destination offers real scientific value, and every choice carries consequences measured across decades. But the existence of those trade-offs does not erase the philosophical weight of what remains undone at Uranus. Because we are living in an unusual moment of history. For almost all of human existence, the planets were unreachable lights crossing the sky. Even imagining travel between worlds belonged more to mythology than engineering. Only within the last century has humanity possessed the capability to physically visit another planet at all. That capability is still fragile. The idea that oceans may exist beneath the frozen surfaces of Uranus's moons did not emerge from ancient astronomy. It emerged from modern analysis, from archived Voyager plasma measurements, from space telescopes, and computational models developed within the lifetime of people still working today. The question of whether those oceans could support life is therefore new, astonishingly new. For the first time in history, a civilization exists that can recognize another potentially habitable environment beyond Earth and possesses the technical ability, at least in principle, to investigate it directly. But we have not gone. Instead, we study Uranus from a distance of billions of kilometers, gathering reflected light through telescopes, orbiting Earth, or resting on mountaintops. We infer hidden oceans indirectly. We estimate magnetic structures mathematically. We reconstruct atmospheric chemistry through spectroscopy, reading wavelengths rather than touching the world itself. Necessary methods, powerful methods, but still distant ones. This hesitation is not unique to planetary science. It reflects something broader about human institutions. We are generally drawn toward problems that produce immediate results, visible outcomes, and familiar forms of progress. Uranus resists all three. Its seasons unfold across generations. Travel times consume decades. Even the scientists proposing missions today may retire before the data arrives home. And yet the unanswered questions remain there, patient and unchanged. Every generation that passes without returning to Uranus inherits the same choice: continue observing from afar, or commit the immense time and resources required to truly enter the system again. Neither choice is irrational, but they are not equivalent either. One path accepts distance, the other attempts to cross it, believing that somewhere in the cold darkness around Uranus may exist discoveries no other place in the solar system can offer. Far beyond the orbit of Saturn, beyond the regions most spacecraft have ever crossed, Uranus continues its slow movement around the Sun exactly as it has for billions of years. Long before Earth carried forests, or animals, or human beings, that tilted world was already there, rolling sideways through the dark. It was there before complex life emerged in Earth's oceans. It remained in place while continents shifted across the surface of our planet, while mountain ranges rose and eroded away, while extinction events erased entire branches of life. Uranus completed its silent orbit while dinosaurs appeared, ruled the Earth, and vanished. Nothing about its motion hurried. When the first human beings looked upward and attached stories to the lights overhead, Uranus was already following the same 84-year path it follows now. Invisible to the naked eye for most observers, it remained indistinguishable from the background stars until William Herschel pointed a telescope toward it in 1781 and realized one of those lights was not fixed at all. A new planet entered human awareness. In the centuries since, we have slowly assembled an image of what kind of world it is. Not a simple gas giant, like early astronomers expected, but something stranger. A planet tipped almost completely onto its side, a world colder than Neptune despite being closer to the Sunday. A system of black rings, chaotic moons, displaced auroras, and magnetic geometry, unlike anything else in the solar system. Inside it, pressures rise into millions of atmospheres. Water may exist in superionic states, crystalline and liquid simultaneously. Carbon may descend through the interior as diamond rain. Beneath the icy crusts of distant moons, hidden oceans may persist in darkness, warmed only by gravitational stress and radioactive decay. And nearly everything we know came from one spacecraft. 6 hours of close observation in 1986 provided the foundation for decades of planetary science. Since then, telescopes orbiting Earth and observatories on mountaintops have added details slowly, carefully, from across billions of kilometers of space. But Uranus itself has remained patient. Its poles continue alternating between decades of sunlight and darkness. Its magnetic field still tumbles through space in distorted spirals. The moons continue circling silently through dim sunlight that takes hours to arrive. There is something humbling in that scale of indifference. Human civilization changes rapidly. Technologies appear and disappear within decades. Institutions rise, reorganize, and fade. Meanwhile, Uranus waits with the calm persistence of geological time, unchanged by whether anyone is watching. The strangest large planet in the solar system has now gone 40 years without another visitor. It may wait 40 more. And if a spacecraft finally returns, after the funding debates, the engineering work, the launch, and the decade-long transit outward, Uranus will still be there, exactly where celestial mechanics predicts: tilted, cold, unresolved. Perhaps that is the deeper lesson waiting at the edge of the solar system. The universe does not hide its mysteries from us, they remain present the entire time. The real question is whether we decide to cross the distance required to meet them.